we continue with our review of the mid semester questions, and let us proceed with that. So, the question that now we will address is as follows. You have 3 parallel plates and the y axis having its origin at the bottom plate. The top plate moves towards the right with a velocity of capital U, the bottommost plate is stationary, and in between, not at the midway, but roughly at 1/3. So, exactly at 1/3 of the distance between the plates, that is if the total distance between the top and the bottom plate is h, then at h by 3 from the bottom plate you have another plate, and this plate is very much similar to the other plates. Of negligible thickness, and this is also moving towards the right with a velocity capital U. So, the description of the flow is as follows. You have steady fully developed flow, steady fully developed flow between the plates with the inlet pressure same as the outlet pressure. Assume the fluid to be Newtonian and uniform of uniform viscosity. You have to determine the velocity profile, that is small u, which is the velocity along the x direction, divided by capital U as a function of y by h. This you have to find out using finite difference, finite volume and finite elements method. You can take any arbitrary choice of the grid layout or the mesh layout as per your convenience. So, let us try to first address the problem in terms of its fundamental governing equation. So, we start from the general conservation equation, that is so if you consider phi equal to u, it becomes the x momentum equation. Phi equal to u, gamma equal to mu, and s is negative of the pressure gradient along x. So, you have there is no extra body force along x. So, this is the momentum equation. Now, we can make certain simplifications. We can consider this term to be 0 because it is steady flow. We can also use the continuity equation along with this one to simplify this term. We will not go through the details of that, but you can simplify this. If you want, we can also of course go through the details. So, this will be so you can club up rho into u as one term and u as another term. So, and use the product rule. So, it becomes rho u del u del x plus u del x of rho u plus you can club up rho v as rho v del u del y plus u del y of rho v plus rho w del u del z plus u del z of rho w, and that is essentially rho u del x plus v del u del y plus w del u del z plus u del x of rho u, similarly del y of rho v and this term is 0 because that is the continuity equation. Whatever is there in this square bracket, that is 0. So, the left hand side is there rho into u del x plus v del u del y. It is a 2-dimensional flow first of all, it is a flow in a plane. So, the third component is not important. Then fully developed flow means del u del x equal to 0. So, this will be 0. If you are considering an incompressible flow, the continuity equation is even more simplified than this one. It will become so del u del x equal to 0 means you have del v del y equal to 0, that means v is not a function of y. We can say that v is equal to 0 at y equal to 0 by virtue of no penetration boundary condition at the wall, say bottom wall as an example, which implies that v is equal to 0 for all y. So, it is also a consequence of the fully developed flow that v is identically 0. Therefore, the left hand side becomes 0. Right hand side, if you simplify, mu is a constant which is given. So, it will be mu because of 2-dimensionality, the last term is not there. Because it is fully developed flow, del u del x equal to 0, so its second order derivative is 0. And because it is fully developed, u is a function of y only. So, this will become ordinary derivative. So, to summarize the simplification, what we have at the end, we have mu regarding the pressure gradient, we can use the y momentum equation to check that there is no pressure gradient along y. So, only pressure gradient that acts along x, so therefore this will become dp dx, instead of the partial derivative it will become the ordinary derivative. So, this is equal to dp dx. Because the left hand side is a function of y only and right hand side is a function of x only, they are equal only when each is a constant, otherwise that is not possible. So, this is equal to a constant, that means you can write this, because dp dx is a constant, you can write it as delta p by delta x, because dp dx is a constant means p versus x is linear. So, this is equal to p out minus p in by the length of the channel. Because it is given that the boundary condition p in equal to p out, that means these are equal, so this is equal to 0. So, finally we are left with the governing differential equation, that d2u dy2 equal to 0. So, the first step of solving the problem is to come up with this simplified governing differential equation with appropriate logic based on which this equation evolves. So, once this equation is there, next we are interested to solve this equation by different methods. Now, what you can see here is that you have the domain between 0 to h, and in between a plate is inserted which is moving at the same velocity as that of the top plate. So, you have a sort of imposed condition in between the physical extremities of the domain, and to handle that you can divide this entire problem into two parts. One is the bottom half which is h by 3, another is the top half which is 2h by 3, and you can normalize this by writing a non-dimensional u. So, define u non-dimensional as small u by capital U and y non-dimensional as y by h. So, d2u dy non-dimensional square equal to 0. So, we have two subdomains. One subdomain is y between 0 to 1/3 and another subdomain y between 1/3 to 1. Just to help in writing, we will omit the bar at the top and we will write d2u dy2 equal to 0, but we will keep in mind that is u bar and this is y bar, just for the sake of writing we are doing that. So, let us consider the part of the domain between 0 to 1/3. So, this is y equal to 0, this is y equal to 1/3. If you want to capture a variation within this one, what is the minimum number of grid points that you could take, and we will take that. So, 2 must be there at the two boundaries because boundary condition has to be implemented, and you at least should have one in between to see what is there inside the domain. So, you can call this as say I, or maybe this one as I, this one as I minus 1, this one as I plus 1. So, for finite difference you can use different schemes, say you use a central difference scheme. So, that is also your choice. If you use a central difference scheme, then d2u dy2 equal to 0, this will imply what? U I plus 1 plus u I minus 1 minus 2 u I by this is delta y. This is 0. So, u I is u I plus 1 plus u I minus 1 by 2. U I minus 1 and u I plus 1 both are given by the boundary condition. What is u I minus 1? So, for y between 0 to 1/3 u I minus 1 is 0, u I plus 1 is not 1, okay, non dimensional, yes. So, non dimensional 1, so which means u I is equal to half. So, your velocity profile in the bottom part at y equal to 0 it is 0, at y equal to 1/3 it is 1, and at y equal to 1/6 it is half. So, it is a straight line. You may plot u along x and y along y. What about the other part of the domain? You can use the same discretization. So, for the other part of the domain it is y between one-third and y equal to 1. So, you can take another grid point in between. So, again you can give these generic names I minus 1, I plus 1, and here also you will get governing equation is still the same. So, u I is equal to u I plus 1 plus u I minus 1 by 2. What is u I minus 1? Capital U. What is u I plus 1? Oh, non dimensional of course, so it is 1. I minus 1 and I plus 1 both are 1, so this is equal to 1. So, it is a uniform velocity profile in the gap between those plates, between the middle plate and the top plate. So, this is 1. Because the approximation of the Taylor series has been based on up to a linear term and the actual profile variations are linear, these actual solutions are linear. So, you get exact solution and the numerical solution the same, because the exact solution also is a linear velocity profile. Then let us look into the corresponding problem with the finite volume method. So, finite volume method, this is like the point I is like P, I plus 1 is E and I minus 1 is W. So, integral, the first step is integrate the governing differential equation with respect to the variable, here it is y, from, so your control volume phases are, this is small w and this is small e. So, integrate from small w to small e, this is equal to 0. That means you have du dy at small e minus du dy at small w is equal to 0. If you consider piecewise linear profiles, then this will become ue minus up by delta y minus up minus uw by delta y is equal to 0. So, up becomes half of ue plus uw. You can see that it is exactly the same as the finite difference discretization equation. Because the discretization equation is the same, the solution is also the same. So, we need not go into the solution again, you will find the same velocity profile, that it is up to 1/3 like this and then up to 1 it is a constant. The agreement between the finite difference and finite volume method is not surprising, because both in effect have considered a linear profile, one through the Taylor series and another through a direct profile assumption. So, because both have considered implicitly or explicitly a linear profile, the consequence, the outcome is the same. Then let us look into the finite elements method. Let us consider any two of the plates, either the bottom two pairs or the top two pairs, any of these two pairs, and let us take some elements. So, how many elements minimum you require? 2, because you should at least have one node in between. Of course, the answer is not correct that how many elements you minimum require is 2. You minimum require a number of elements 2 provided each element has 2 nodes. What happens if one element has 3 nodes? Then you could have taken just one element, but then you should have required a higher order interpolation function, a higher order shape function. But if you want to use linear interpolation function, then your unknowns per element will be 2. So, that means you will have 2 noded element, then 2 such elements at least will be required. So, the minimum number of elements required will depend on the order of the polynomial that you are using for interpolating the function. If you use a higher order polynomial, then you can use a single element, but maybe with some interior node points within the element to accommodate the higher order interpolation function. But here we will use linear element. So, one element, say let us give some names, numbers 1, 2 and 3. So, one element number 1 is 1 2, element number 2 is 2 3. So, for each element let us formulate the finite elements equation. So, what is the first step? You integrate it with respect to y after multiplying with a weighting function, let us say v is the weighting function, we are using the Galerkin's method. And then we integrate it by parts if it is possible, because that will reduce the requirement of the continuity in the order of the highest order derivative. Because we have used a linear element, at the most first order derivative we can accommodate. So, let us consider that one. So, we integrate it by parts by considering v as the first function and d2u dy2 as the second function. So, v into du dy, let us consider any generic element. So, from I to I plus 1, say some generic element which has two nodes, one node number I, another node number I plus 1, minus integral of derivative of first into integral of the second. Next we have to develop the shape functions n1 and n2. So, what we do, we describe u as a0 plus a1y, and we know that u equal to u1 or ui at y equal to yi and u equal to ui plus 1 at y equal to yi plus 1. So, ui is equal to a0 plus a1 yi, ui plus 1 is equal to a0 plus a1 yi plus 1. So, from these two we can find out a0 and a1. So, to find out a1 we just subtract. So, a1 into yi plus 1 minus yi is equal to ui plus 1 minus ui. So, a1 is ui plus 1 minus ui by yi plus 1 minus yi. We can find out a naught as u1 minus a1 yi. So, ui minus ui plus 1 minus ui by yi plus 1 minus yi into yi. So, it is ui yi plus 1 minus ui plus 1 yi by yi plus 1 minus yi. So, u equal to a0 plus a1y. So, ui, so let us first collect the terms with ui. So, ui into what? Ui into a0 plus a1y. So, ui into y I plus 1 minus y by y I plus 1 minus yi. This is with ui, and ui plus 1 plus u I plus 1 to y minus yi by yi plus 1 minus yi. Okay. So, this if we call as ni ui plus ni plus 1 ui plus 1, then obviously this is ni and this is ni plus 1. Whether the derivation has been fine or not, we can check that ni should be equal to 1 at y equal to yi and 0 at y equal to yi plus 1. Similarly, ni plus 1 should be 1 at I plus 1 and 0 at I. So, you are what you are doing essentially is you are writing that u is equal to ni plus 1 ui plus 1, this is what you are writing. Okay. So, we call it n into u matrix into u vector. In the Galerkin's method, the trial function and the weight function are the same. So, V is also ni Vi plus ni plus 1 Vi plus 1. So, you can write this as Vi plus 1 into ni plus 1, just in the transpose form of the previous one, because that will help us in matrix manipulation. Let us substitute those here. So, in place of V we write Vi plus 1 into ni plus 1 multiplied by du dy at I plus 1 minus integral of I to I plus 1 dv dy. So, again we can put Vi plus 1 and this will become dni dy dni plus 1 dy, because n's are functions of y but v's are not functions of y. Similarly, in place of du dy you can write dni dy dni plus 1 dy dy. So, into ui plus 1, which are your unknowns that you need to solve. Now, considering that each element has length dy sorry delta y, that is yi plus 1 minus yi equal to delta y. So, what is dni dy? Minus 1 by delta y. So, this is minus 1 by delta y, this is plus 1 by delta y, this is minus 1 by delta y, this is plus 1 by delta y. The next step what we do, we consider that these variations are arbitrary. So, essentially we can forget about this and write the terms as if we have cancelled the variations from the both the terms. Arbitrary most importantly, but not 0. If they were 0 then it would have been division by 0. Now, ni into du dy, what is ni at I plus 1? 0, ni plus 1 at I plus 1 is 1. So, this will become, the upper limit will become 0 1 into du dy at I plus 1. right, we are writing the upper limit minus the lower limit. So, this is like this evaluated at I plus 1 minus the same thing evaluated at I. So, this evaluated at I plus 1 minus the same thing evaluated at I. So, at evaluated at I, this will be 1 times du dy at I, and this is 0. Okay. So, this is the boundary term minus 1 by delta y square, then 1 minus 1 minus 1 1, there is 1 by delta y square, then there will be one integral of dy. So, that will be delta y, so 1 delta y will remain, right. This into ui ui plus 1 equal to 0. So, the first two terms, the boundary terms, we can write together as minus du dy I and plus du dy I plus 1. Okay. Next what we will do, so this is for each element. Now we will assemble the two elements. One is element number 1 where I is 1 and I plus 1 is 2, then element number 2 where I is 2 and I plus 1 is 3. So if we assemble this, then we can write minus du dy 1, next term is du dy 2, we will add the effects of the second element subsequently, but first let us write the corresponding entries. How many entries are there? 3 entries here, because there are 3 nodes and the corresponding stiffness matrix will be 3 by 3. Okay. So then for the, let us write for the first element, 1 and 2. So 1 minus 1 minus 1 1. For the second element the points will be 2 and 3. So it will be minus du dy 2, this will be plus du dy 3, minus I and plus I plus 1. So I is 2 and I plus 1 is 3. Here it will cover 2 and 3, so 1 minus 1 minus 1 1. Our objective is to solve for u2 because 1 and 3 are located at the boundaries, no matter whether it is top half of the domain or bottom half of the domain. So you can see that this becomes 0. So for the second equation, what you get, equation number 2. So here basically you will get 3 equations, one for u1, one for u2, one for u3. Equation for u1 and u3 you do not require because there you have boundary conditions, values, you have Dirichlet boundary conditions, that is specified values of u1 and u3, but you require the equation for u2. So what is that? Minus 1 into u1, so minus u1 plus 2 u2 minus u3, that is equal to 0. That is the equation 2 from this system of equations, that is u2 is equal to u1 plus u3 by 2. Again after so much of effort you can see that you get back the same equation as what you got for the finite volume or finite difference, that is the midpoint is the average of the 2 points located in the boundary. And this is also not unexpected because Here also you have considered a piecewise linear profile, which is the shape function or the interpolation function in the language of finite elements. So, because you have considered a linear profile, you will get the same consequence as that you get using a linear profile from a finite difference or a finite volume. It is a linear problem, so it does not have any scope of having any other variation. So, you can see that this is a simple example where through different approaches we merge to the same answer, and with the same profile assumption either explicitly or implicitly we get back the same outcome from a very simple governing differential equation. Okay. So, this is about the discussion on the questions that we had for the mid semester examination. Now, so far we have discussed about one dimensional problems, but in reality we know that problems are 2 dimensional or in the most general case 3 dimensional. Therefore, we need to graduate slowly from 1 dimensional to 2 dimensional or maybe possibly 3 dimensional. We have to keep in mind, however, that if we increase the dimensionality, the basic principle of solution of the problem does not change, and that is why 1 dimensional problem is so important to get a grasp on the or grip on the method of solution, because once you understand that, it is a straightforward extension of that to multiple dimensions that one is looking for 2 dimensional and 3 dimensional problems. We will illustrate this for the case of finite volume method for 2 dimensional unsteady state diffusion problem. So, what is our governing equation? Let us take the example of heat conduction. Rho Cp del T is equal to this one. So, we need a grid layout for the finite volume method. Now, it is a 2 dimensional problem. So, our control volume is like this with P as the central point, E and W are east and west grid points. Now, it is a 2 dimensional problem. So, if this is x, this is y, along y direction we have grid points N and S, north and south. The control volume faces are represented by small letters. So, small e, small w, small n and small s, and various dimensions are given as follows: delta x e, delta x w, delta y n, then delta y s, delta x and then delta y. So, what is the first step? Integrate the governing differential equation with respect to all the variables, so time and spatial variables. So, let us call this as term 1, this as term 2 and this as term 3. If you want to put a source term, let us put a source term also, term 4, to make it very general. So, for the term 1, what it will give? Integrate it with respect to time x and y. So, from time t to t plus delta t, what is the limit of x? small w to small e, what is the limit of y, small s to small n. So let us do the integrals one by one. First we consider the time integral. So this will be rho Cp into t at time t plus delta t minus t at time t. So this will be rho Cp t minus t0. At time t plus delta t we use without any superscript, as we have considered for the one dimensional unsteady state problem, same notation we are using, minus t at the old, so t at present minus t at the old time step. So this dx dy, so when we integrate this with respect to x, what is the profile assumption that we can take for this? We can take piecewise constant, because there is no derivative, we need not take it as something different from a constant. So if it is a piecewise constant temperature profile within each control volume, then this T becomes Tp. So with respect to x, if we integrate, the next step will be, it will be rho Cp Tp minus Tp naught, this whole thing is a constant, so it will come out of the integral dx will become x e minus x w, x small e minus x small w is what, delta x, and that integrated with respect to y is delta y. So that is the term 1. Let us consider term 2. So integral dx dy dt, x from small w to small e, y from small s to small n, time from t to t plus delta t. Now this of course depends on what is the time integration scheme that we are using, but before that let us consider the spatial integration. So first this integral, so it will become k del t del x at small e minus k del t del x at small w, right. What kind of profile you can take? Piecewise linear. So you can see that it is basically a locally one dimensional calculation that you are doing and adding a dimensionality over that. This is a local one dimensional calculation. So it will become k dt dx at small e minus k dt dx at small w. So I am writing it in one step. So it is k e into T e minus T p by delta x e minus k w into T p minus T w by delta x w. So the final term, by considering the entire integration, will be what? This term integrated with respect to y into delta y and integrated with respect to time. So integral of t dt, it depends on what scheme you are using, explicit, implicit or Crank-Nicolson. So let us consider a fully implicit scheme. Remember, this discretization will be different if you consider any explicit scheme or Crank-Nicolson scheme like that. So you consider this as a fully implicit scheme so that the temperatures remain this one and only you are multiplying by delta t, because in the fully implicit scheme the temperature remains temperature at the end of the time step, that is taken as the value of the temperature throughout the time step. Similarly, what will be term 3 we can write now easily by analogy with the term 2. So let us just complete it. So, dy dx dt, so y is from small s to small n, x is from small w to small e, and t is from t to t plus delta t. So, what will be the corresponding term? In place of k small e, it will be k small n into t n minus t p by delta y n minus k small s into t p minus t capital S by delta y s into delta x into delta t. So, here also what you do, you first integrate with respect to y, and then with respect to x and with respect to t, because it is fully implicit, t remains same as that at the end of the time step. Okay. And for the term 4, you can consider s as, term 4 is integral of s, you can consider as sc plus sp tp into dx dy dt, x from small w to small e, y from small s to small n, t from t to t plus delta t. So, what it will become? Sc plus SPTP will be a constant with respect to all those integrals. So, remember we are considering a linearized source term, so that we are able to write it in this form, this into delta x, delta y, delta t. So, we have got all the 4 terms. The final job is to assemble these terms. So, to assemble these terms, what we do is we divide all the terms by delta t. We divide all the terms by delta t. If we do that, we will get the equation of this form. In this form. So, let us try to fill up the corresponding coefficients. What is AE? KE by delta x E into delta y. Okay. What is AW? KW by delta XW into delta y. AS Ks by delta ys into delta x, an kn by delta yn into delta x, ap0 rho cp into delta x into delta y by delta t, AP AE plus AW plus AS plus AN, then plus rho Cp delta x delta y by delta t, then there is one Sp term minus Sp into delta x into delta y, and B is Sc into delta x into delta y. So, what we can see is that this equation also can be cast in the same form as that of the generic form that we have developed for a one dimensional problem. What is that? APTP is equal to summation of A neighbor into T neighbor plus B, where here there are 4 space neighbors and 1 time neighbor. This casts the system into a system of linear algebraic equations, but now there are 4 neighboring spatial neighbors and 1 temporal neighbor. So, those appear instead of a fewer number of neighbors for a one dimensional problem. That is the first observation. Second observation is that you can see the physical significance of various coefficients. What is this AE for example? What is this delta y? Delta y is, so this length is delta y, length perpendicular to the plane of the figure is 1. So, unit width is considered. So, delta y into 1 is the face of this area. So, it is just like conductivity into area of the face by length, Ka by L. What is that? Conductance. Inverse of that is resistance, thermal resistance due to conduction, L by Ka. This is Ka by L. Okay. So, these coefficients physically represent thermal conductances of various phases. And the other important thing that you may observe here is that this is an unsteady problem, but you can convert it into a steady problem by setting delta t very large, because if delta t tends to infinity, then the extra terms which come out of unsteadiness become 0. So, this is some trick that many times we play. Say you have a program which is given to you or which you have developed for an unsteady problem, but you want to use the same program for a steady problem. What trick you can play? Just use the same program, set artificially delta t equal to very large, so that the term which contains delta t will become 0. So, to summarize, we have now got an idea that how to develop the discretization equation for a 2 dimensional problem. I give you a homework that you do the same thing for a fully explicit scheme. We have done it for a fully implicit scheme, you repeat the same exercise for a fully explicit scheme, and similar extension you can also do for a 3 dimensional problem. So, till now we have seen what is the basic principle of discretizing diffusion type of problems in 1 dimensional, 2 dimensional, or even this can be extended to 3 dimensional. At the end we get a system of algebraic equations. Our next objective will be to see that how to solve this system of linear algebraic equations that we get from this discretization, that we will take up from the next lecture. Thank you.